Okay, good morning. So today we will continue our discussion still about the ideal Bernoulli in the fluid flow. So on our last lecture, we already have discussed about different types of fluid flow measuring device. Okay, starting from the pitot tube, this is to calculate or to measure the flow rate of the plane by putting a very small tube on the plane that by using the principle of the Bernoulli and also with the mass balance equation, then you can find the correlation how to get the velocity. Basically, you correlate the velocity you calculate the velocity by measuring the different pressure that's showed by the manometers. So it's like converting the velocity into the static pressure and you calculate the height difference. With the same principle, you can use the orifice. Orifice, the principle is also the same. You change the velocity, but in orifice, the changing in velocity are caused by what you call the orifice, the small opening inside the pipe. So you can have the correlation for calculating the velocity as well. And also the same for the venturimeters. So basically, by changing the diameters inside the pipe, you can change the velocity and also you can change the pressure. So change of pressure can be measured directly by putting the manometers. That's all that we have discussed on our last lecture. The other types of flow measuring device is what we call rotameter. Have you ever seen these types of device? Maybe somewhere during your high school or during your TPB?
No, sir.
No, never?
No, I
Not
haven't,
once?
sir.
No.
Okay. Later, when you have lab tech, the laboratory technology in your third year, or maybe on your, I don't know, for your MPA class, but for the lab tech, some devices are connected to the rotameter. Basically, the rotameter calculate the flow of gas. Mostly it's used for the gas, but sometimes it's also used for liquid. And the fluid will flow from downwards. So what happened when the fluid flowing from the downwards? Inside the rotameter, you have, how to call it, like a ball. Sometimes the shape is really ball, sometimes the shape is like a bullet. So like this one. So when you have gas flowing from the downwards, then it will lift the ball until the ball is steady on certain position, and you can see in outside tube of the rotameters, you will have scale, and you can read how much is the flow rate. Like this one, you can see the numbers, right? So basically, in rotameters, you will have this kind of arrangement. So for this one, the tube is not similar diameters throughout the flow, but the diameter will slightly increase. And like I have explained before, the gas will flow from the downwards, and then it will lift the ball until certain position. And in this position, you remember again, right? If the ball are in a steady condition, then the resultant of force will be 0. So the resultant of the force will comes from the weight force, right? Weight force should be similar or should be same with the buoyancy force. So the basically this is the application of the buoyancy force. And you do you still remember what is actually the buoyancy force?
It's the force from below, sir.
It's the force from below. Can you explain more?
Force from below minus the weight minus the wait, the force from above. Is that right, sir?
Okay, buoyancy force is the force that given by the fluid, right, to compensate the weight force, right? And this is the the force that given by the fluid to compensate the weight force. So the direction will be upwards while the weight force is downwards. But actually, the buoyant force is the what? Is the delta or is the selisih of?
Is it density?
No, not density. Do you still remember? If
The, the, is it the difference in pressure from below and above, sir?
yes, correct. So the buoyancy force is actually the difference between the pressure force between the upward pressure force and downward pressure force. So please remember again, if you already calculate the buoyancy force, you do not need to calculate the pressure force because it's already replaced by the delta between the pressure force from above and pressure force from below is already calculated in the buoyancy force. But in these rotameters, those principle, the pressure force or the buoyancy force are used because when the gas is lifting up the ball until certain position, there will be some differences in the pressure from above and also from below. The higher the flow, because in buoyancy itself, when we study about the buoyancy force, we always consider the fluid are in a static condition, right? So this one, the buoyancy force that in previous discussion, the fluid is not moving. So the fluid is only giving the buoyancy force to the ball as the opposite direction of the weight force. But in this rotameters, because there is some flow from below, the direction is upward, then it will create different forces with different velocity of the gas, right? So it will create different forces, but the weight force are remain the same, right? So basically, the higher the velocity, the forces given from the below are higher. How about the forces given from the above? Same, right? So the force given by the fluid from above the ball will be the same. But the forces, regardless the velocity of the gas. Okay, but the forces given from below the upward direction will be depending on the velocity of the gas. These principles are used to calculate the flow rate. It means the higher the velocity, the ball will move upward until certain position, and then it will steady. So there will be some, you call it calibration with the scale that you can read from the rotameters. Basically, this is the principle. I will not explain how to derive the equation since it's not necessary for this class. But for this one, you need to remember the basic principle of the rotameters. Okay. Any question about this one? So if later you enter the lab and you see this kind of device, please remember that the name is rotameters. Okay. Okay, any question?
Sir, I have a
Yes.
question, sir.
Okay.
With the difference in the diameter of the rotameter, does it affect, sir?
Yes, of course. Because if you see from above, if you see from the side, it will be like this, right? Okay. But if you see from the above, it will be like this. So if the diameters of the tube, this one is the tube, this one is the tube. The space between the wall of the tube and the ball will be uh, different depending on the position of the ball. The higher the position, and then the space between the wall and this one will be larger. So it will create the pressure difference as well from the above and from the below.
How do we put it in calculations, sir?
Actually, there is some derivation, but I do not show in this slide. But if you need, then I will give you the full calculation later.
Will it be tested, sir?
No, that's why I did not put it in this slide. It's
Okay, sir.
it's quite a complicated equation.
So what's important here is just the buoyancy force, right, sir?
Yes, the principle of the rotameters and how rotameters can be used to calculate the flow rate. Basically, if you see from our discussion last time about the Venturi meters and then orifice meters of the pipette tube, basically how to calculate the velocity of the fluid is by creating the pressure difference, right? At 2 points at the pipette tube, and then in the pipette tube, you calculate the pressure difference between the outside condition with inside the tube. But for the rotameters and the venturi, you create the pressure difference by changing the diameters inside the pipe. In here, in the rotameters, you create the pressure difference by increasing the velocity by changing the space between the tube and the ball.
Sir,
Okay.
in the formula of the buoyancy there, it's rho g VB. What's VB again, sir? Is it the volume of the ball?
Yeah. VB is volume of the ball. This one is density of gas or density of fluid, right? But this one is density of the ball. Because
So
this
it's like F equals to mg gitu, sir?
yes, correct. Because all the ball are inside the fluid, right? So the condition is always when you calculate the buoyancy force, the volume is always the whole volume of the ball.
Sir, if we wanted to do it step by step, P3 itu, how do we get P3, sir?
Okay, P3 is the pressure from above, right? So it should be F from above divided by the area. However, since this is the ball, the area is not two-dimensional area, right? Because it's like half part of the ball.
Yes, sir.
That's why the calculation is a bit complex. And if you analyze like this height and this one, area will be different, right? And also the area of the remaining space between the ball and the tube, for example, this one, will also be different. The same as well as pressure from below.
So if in like quizzes like that, sir, will it just be given the pressure from above will be this much gitu?
Sorry again.
Will the pressure be given, sir? Because it's like complicated, sir.
It's not given the value of the pressure, but you need to calculate first the force, and then you have to divide by the integration of the area. That's how you calculate the pressure. But if you want, then I can show you the slide, but I need to find out later. So I will send it to the WhatsApp group. Is that okay? Then if you have question, then you can discuss it later.
All right, sure, sir.
Okay. Okay. This is the types of the fluid flow, the velocity of the fluid flow. Okay, this one actually I already put in the homework, but have you tried? Have someone try this exercise? So basically, you comparing you are using the Bernoulli equation between position 1 and position 2. Position 1 is here. This is 1. And position 2 is this one. This is Venturi, right? But you put it vertical. And then, do you still remember the component of Bernoulli equation?
Potential energy, kinetic energy, and pressure energy, sir.
Yeah, in formula, if you want to do it in head, for example, P1 divided by
Rho G
rho G plus that
plus
one, right?
M or Z ya,
P or
plus
H, okay,
yeah.
G, right? Please don't forget this equation. This one. This one, right? Okay,
Yes, sir.
Z1 is here. Z2 is here. So if you take the baseline of the position at point 1, then you can use Z1 equals 0.
Tapi sir there's a difference in height, sir.
Yes, of course, because the oil are moving upwards. It's different between the Venturi that we have discussed before. In the Venturi that we discussed before, the position is horizontal, right? So there will be no differences between Z1 and Z2. But in this case, the flow are upwards, vertically upwards. So there will be difference in potential energy between point 1 and point 2.
Okay, get it, sir.
Okay, so just take point 1, for example, as the baseline for the position. So it will be equal 0. And then what next? You need to calculate the volumetric flow rate. This is debit. Debit will be
Density times Q.
debit is volumetric.
Tariknya ketukar sir. Area multiply by linear velocity ya.
Yes, correct. Please don't forget the okay. Either you calculate velocity at point 1 or velocity at point 2. Then how you correlate velocity at point 1 and point 2?
Langsung dibarit by A1, sir.
Yes, you can use or you can correlate its velocity by using the ratio of the area, right? Then you can put in this equation, just replacing either velocity at point 1 or velocity at point 2 using this one. Okay, how about P1 and P2?
Itu sir, rho GH of the manometer.
Yes, correct. So which one is higher?
0.1 is higher.
Okay, P1 will be higher than P2 because the direction is upward, right? And you see that the manometers, the fluid inside the manometers yang diarsir ini, the head is higher on the left side. So P1 minus P2 will be equals to rho GH in the manometers. This one is the fluid of the density of manometers fluid. Okay, then you will have the value of delta P, P1 minus P2. Okay, then you can solve either velocity at point 1 or velocity at point 2. Then you multiply it with the area. Okay, any question about this homework? Then you can do the calculation by yourself.
For Venturi meter, the pipe is always a cone lagi. Circle, right, sir?
Oh
the
yeah.
area is always an area of a circle, right?
Yes, in this arrangement, the area will be circle. Correct. But please remember that the diameter is different.
Also, sir, since it's given that the SG is 0.9, so the density is like 900. Is that right, sir?
Yep, you can use density of water is 1,000, this one. So SG of the oil is 0.9, then the density will be 900 kilogram per cubic meters. Also in the manometers, the density, the SG is 13.6, so it will be 13,600. Okay.
Sir,
Ya, silakan.
So if just want to make sure if the flow direction goes downward, then the P2 will be bigger than P1, right, sir?
Yes, it will be vice versa.
Okay, thank you, sir.
Okay, any other question? Okay, if you have no other question, I think the second number will be this one, right? So I think this one should be easier than previous one. Maybe just small correction that this point should be closer to the orifice. So you will have water close to the orifice, and then the density is known. Then, but in the manometers, so the blue one is water. This one is water. And then in the manometers, it is filled with 3 different types of fluid. We call it A, B, C, and the value of the density in terms of specific gravity is this one. So fluid A is 2,500, fluid B is 1,500, and fluid C is 1,200. Then by applying the Bernoulli and then applying the hydrostatic pressure, please remember in the manometers the conditions are static, all the fluids are in static condition. Then you can calculate the pressure difference. Pressure difference means pressure between this point and this point. This one should be more straightforward. You know how to calculate, right? You just put 2 points which have Still remember, in the hydrostatic concept, 2 points will have same hydrostatic pressure if
the fluid is the same and the height is the same, sir.
yes, correct. So if the fluid is the same and the height is the same from some baseline, then it will have same hydrostatic pressure. At which point, if you see this kind of arrangement,
in the border of the white fluid and the purple fluid and the white fluid and the orange fluid, the pressure will be the same, sir.
okay, you can take this one, this point, or this one. If you take the above one, then you do not need to consider the density of fluid B, right? Because the baseline is here. But if you use this baseline, then you need to consider the density of fluid B. Just be careful with the SG is different. Any question first before we continue to our next discussion?
Sir, so over here, all you have to do is just rho GH of A and rho GH of C and find the difference.
Yep, but you still have water, right, in this part?
Kayaknya ngedadak amnesia deh, sir.
Why?
I forgot how to solve these kinds of things.
Yeah, because at point let's call it point 1 and point no, 1 and 2 is over there. What you need to calculate is P1 minus P2, right? How much? This is the pressure difference. Then if I put it like point 3 and 4 here, then point pressure at point 3 will be the same as pressure at point 4. Pressure at point 3 is pressure at point 1 plus rho water G delta H water plus rho A G delta H A. And this one, and the left, right? This is left. This one is P2 plus rho water G delta H water at the right leg, I mean, plus rho C G delta H C.
Tapi height-nya nggak dikasih tahu sampai atas, sir.
Yeah, then you can correlate by using these figures, right? This is 5 centimeters. The above is 7 centimeters. So this one should be the same, right?
Iya, sir, benar.
Yes. Then just assume it like X centimeters, and then you can cancel out. You can divide it the rho water times G times delta H water into two parts, like the first leg of water, which is the same with this one, and the second leg, which is 7 centimeters. Bisa kan ya?
Oke, sir.
Okay. So the rho GH in this part will be the same, right?
Yes, sir.
So that is the trick of the question.
So itu bisa kan sir until the same height as the orange liquid. Tapi gara-gara liquidnya beda, pasti density-nya, pressure-nya pasti beda kan? And you have to find that difference in pressure, right?
Yep. Pressure
Okay.
at this one is the same, but because the density and the fluid the different, then it will create this one. That's you need to calculate. Pressure at point 1 minus pressure at point 2.
Oke, sir. Ngerti, sir.
Okay. Any other question? Okay, if not, then we will move to the slide number 5. I'll stop the recording first.